Okay, welcome to the Wednesday contributed session, room 2. Our first speaker is going to be Ximena Fernández, intrinsic persistent homology via density-based metric learning. So take it away.
Thank you. Thank you for the introduction. I'm really happy to be here. So in this talk, I will talk about a recent work with my collaborators from the University of Buenos Aires. And in this talk, I will show you some issues that may arise when you try to compute persistent homology from a sample, noisy sample of a manifold. And I will show you some kind of strategies to overcome these issues. So let's start with the general problem. So suppose that you have a manifold, a d-dimensional manifold that is embedded in a higher dimensional Euclidean space. But what you have is only a finite sample of points in this manifold. And the question that you want to answer is how to infer the homology of the manifold from the sample. And if you're following the lectures of Peter Bubenik, perhaps the first answer that you should say and now is to compute the persistent homology of the sample. So let's try to apply this procedure in this example. So this is the kind of output that persistent homology gives you. This is a persistence diagram. In this case, each point in the diagram is a generator in homology. Different colors correspond to different degrees. And in the x coordinate, you have the birth of a generator. And in this case, I plot the lifetime of each generator. Okay, so it's a sort of projection of the classical diagram with the diagonal. You project the diagonal into the x coordinate. And you can see that here there are two generators of the first homology group. So this is wrong. What happened? Well, in this computation, we use the Reeves filtration. And we use a distance window. We always sample with a distance that in this case is the Euclidean distance because it's a kind of the first choice if you have points in the Euclidean space. And yeah, and at the level of this distance in 0.5. So at the level of 0.5, this new generator appears. And yeah, we have this property of the Reeves complexes that preserve the homotopy type up to some this amount that is twice the reach of the manifold. And this amount in this case is 0.5, depends on the embedding of the manifold. And this is not what we want, okay? So let's try to fix this problem and use in the computation of a persistent homology an intrinsic distance. Of course, we don't know the underlying manifold, but there is some theory. The KNN, the K nearest neighbors distance that can be computed from the sample is an estimator of the intrinsic distance. The K nearest neighbor distance works as follows. So you construct a graph over the points, in this case for k equal to 5, and then compute the distances between the points using this graph. So in this case, we recover the single generator of the first homology group, and you can see that this generator persists longer than in the previous case. And that's because the Reeves complex compute using intrinsic distance preserve the homotopy type of the manifold for up to some parameter that is less or equal than the convexity radius of the manifold. And this parameter, this invariant of the manifold does not depend on the embedding. So this is nice. This is what we want. Okay, great. So let's try to apply this procedure in a noisy sample. So you can see that, in the case, the same procedure has an output, a diagram with two generators of the first homology group, and this is wrong. What's happening? Well, if we inspect the KNN graph, we have here this this kind of shortcut that distort the notion of distance between the points in this area. So let's try to tune or make a different choice of k. If we decrease the value of k to k equal to 4, we eliminate this shortcut, but we have here this this connection. So what's happening here is that the persistence diagram shows a lot of noise at the level of H1, and it's a diagram corresponding to a noisy, very noisy sample, but of a contractible space. And this is again wrong. So let's try to fix this issue. And this motivates an approach based on the density that produced the sample. So we're good with this kind of distances, this kind of intrinsic distances when we compute the persistence diagram, but we need to make this approach a little bit more robust, okay? So this will be our approach. Given the sample of this finite set of points in the Euclidean space, we will assume that the data belongs to a manifold. This is the so-called manifold assumption. But we also will be interested or be aware of the density that produced the sample. So we know, at least in our mind, that there is some function, a density function defined over the manifold that produced the sample. Of course, in the real setting, we don't know the manifold either, and we don't know also the density, but we want to take into account this information in some way. So the strategy will be the following. We will consider a new Riemannian metric and the manifold that depends on the density. Of course, any choice of distance of Riemannian metric does not change the topology, but it changed the output of the persistent homology computation. So that's why we are interested in different kind of metrics. And of course, we need an estimator of this distance because we only have the points, the sample, and we don't have this all this information, for instance, the density. So let's take a look of this new metric that we're going to consider in our manifold. You have a manifold, and if you have a density, you can deform the original metric tensor using the density in this way. This is one kind of option. And this deformation will be quantified with the parameter Q. So if we inspect the formula of the associated Riemannian distance, this is the formula, and you can see that if f is uniform, then this parameter, this weight here, is constant. So we are recovering the original Riemannian metric or distance. But if f is not uniform, then here we're penalizing paths that go through areas of low density, and the amount of this penalty is quantified by this parameter Q. So for instance, in this example, we have these two paths, gamma 1 and gamma 2. And if this area is an area of high density, then gamma 1 under this definition is shorter than gamma 2 because it goes through an area of high density. This formula, or this and this distance, is related to the Fermat principle in optics. So this is why this distance is also called the population Fermat distance. The Fermat principle in optics has a similar formula for the path of light, and the weight is associated to the refraction index. Now, this is at the level of the manifold, but of course we don't know F, we don't know M. So we need an estimator of this deformed metric. So given a sample of points, this is the proposal. So you have a parameter P, and given 2 points, you compute all possible paths over these 2 points using the points in the sample. And you join the consecutive points with a segment, and you compute the length of each path as the sum of the length of each segment, but raised to the power P. So in this way, since P is greater than 1, we are also penalizing areas of low density, okay? So let's try to look at some example of this deformation. So here you have a manifold and a sample. And if you compute the Fermat distance between points in the sample, you can see that you choose a parameter P. And if you try to project again into the plane in order to recover this original distance, this is what you obtain. Here we're using an algorithm called multidimensional scaling. And you can see that as the value of P increases, you can see more clearly the original topology of the manifold. And there is also an effect that makes points in areas of low density that they are transformed into outliers, okay? So, so from a theoretical point of view, what you have is your original manifold and this original deformed Riemannian metric. But in real life, you have data and you have this distance that you can compute from the sample. You have in both cases some parameter, and if you want to obtain some conversions of these distances, the relationship between the parameters is this: Q equal to P minus 1 over D. D is the dimension of the manifold. So what we prove is this result of conversions in the sense of Gromov-Hausdorff of these two metric spaces, okay? We need some rescaling of the sample distance, and we have this exponential rate of conversions, okay? And moreover, if you're interested in the diagrams, in the persistence diagrams, you probably recall the stability theorem for persistence diagram that makes some relationship between the infinite, the Wasserstein distance between the diagrams and the Gromov-Hausdorff distance between the metric spaces. So as a consequence of this theorem, you also obtain, you have the diagrams associated to the original manifold and associated to the sample, and you also have conversions of the diagrams. Okay, this is perhaps too technical, but if you look at some examples, this was our original noisy sample, and if you compute the persistence diagram using this distance for different values of P, you can see that in each case you recover the single generator of the first homology group. And in the level of H1, you can see this effect of the points being in areas of low density becoming outliers, okay? So let's try to understand a little bit more this, this topic of the outliers. So here is an example of, this is a sample of a trefoil knot in blue, and you have some outliers in red, and this is a top view. So what we're going to do is to compute the persistence diagram of the original sample and the sample with plus the outliers for different choices of distance. If you choose the Euclidean distance, it's the same problem as before. You have here 4 generators of the first homology group, and this is the problem of the ridge. The ridge here is small, and you have wrong information. And moreover, if you are outliers, okay? Now, if you use the estimator of the intrinsic distance without any deformation, without outliers, you have 1 generator, right? This is okay, but if you add the outliers, you lose this information, okay? So you have this wrong information. And finally, if you compute the diagram using Fermat distance, you have a single generator without the outliers, and you have this diagram in the case without the outliers. So let's inspect a little bit more this diagram. If you zoom in, so for each degree, you have a different diagram. And if you compare the diagram for H1 with the case without outliers, you can see that these 2 diagrams coincide. And this is not by chance. This always happens under some hypothesis. And if you compute or compare the diagram at the level of degree 0, you can see that this part is similar, it's the same, and you have also a single point, one generator for each of the outliers here. So in some sense, the diagrams without compute from the sample without outliers are related to the diagrams that you compute without the outliers. And there is a proposition that tries to quantify this relationship that says that if you have a sample and you add outliers here, then for positive degree, the diagrams will coincide up to some parameter here, that is delta to the p. That is not a problem because in general, this parameter is greater than some reasonable parameter that you use when you compute or you plot the diagram. In general, you have an upper bound in the diagram, and it's a reasonable choice of an upper bound, the parameter of the filtration, the diameter of the sample, because after this filtration parameter, your Reeves complex is just a complete and simplex, so the homology is trivial. You have a known interesting information after this filtration parameter. Okay, so now I will show you some applications of this approach in signal analysis. So suppose that you have a signal, and a nice approach to understand from a topological point of view a signal is the computation of the sliding window embedding, also called the delay embedding. So you transform a single signal into a curve in RD. So you have to choose two parameters. D is the embedding dimension, and T is the delay that you use to compute the delay embedding. And there is a theorem that says that the topology of this embedding is the same as the topology of the underlying attractor of associated to the dynamics, the underlying dynamics. So for instance, in this example, here you have a signal. This is the x coordinate of the Lorentz dynamical system, okay? So you have two choices. You use the equations that you don't know in general to construct the attractor, or you use the delay embedding to construct this embedding. And you can see that the topology is the same. So we will apply this strategy. This is an electrocardiogram signal. And if you compute the delay embedding, this is the topological space that you obtain. And if you compute the persistence diagram, in this case, we are using Fermat distance because we need this property of robustness. The persistence diagram up to the time 4000 is this one with a single generator of first homology group. And if you compute the embedding up to the value at the time 6000, you have a new generator in the first homology group. So what's happening is that the embedding of the orange part of the signal, this periodic pattern in the signal, is this noisy curve in orange, but this anomaly here is producing a new cycle, okay? This cycle. Moreover, if you repeat this procedure, but you compute the embedding up to some time, and then you compute the persistence homology of the period, say 0 up to time t, you have a family of persistence diagrams that are evolving in time. And if you compare consecutive diagrams, you can see a peak after the anomaly is produced. Okay, so in some sense, you can detect anomalies in the signal from this topological point of view. Now, another example. This is the air sac, the record of the air sac pressure of a canary during a song. So we apply the similar procedure. We have this very nice embedding. And you can see, if you compute the diagram, 4 generators of the first homology group. And moreover, this is the embedding of the entire signal. But if you compute this time evolving embedding and the time evolving persistence diagrams, and you compute the passage time distance or the bottleneck distance between consecutive diagrams in time, you can see these peaks that are followed by this exponential decay. And these peaks are related to the change of pattern, okay? And moreover, you can see that each pattern is embedded as a new cycle in the delay embedding. So what's happening is that, yeah, in a song, a canary has different patterns at different syllables, and we could detect change of patterns and also the different syllables using persistent homology. These 4 patterns are the 4 generators of the first homology group of this diagram. Okay, so that's all. This is. Sorry, this is some references. There is a preprint, a code with experiments, and a library called Fermat that you can use to compute Fermat distance in your favorite point cloud. And thank you.
All right, let's thank Ximena. So who has questions? I have a very basic question. Early in your talk, you mentioned k nearest neighbor distance. How is that defined?
Okay, so let's see if I can write. Oh, let's go to the slide. It's very used in computer science. And the idea is the following. Let's go. There. So the idea is the following. So for each point, let's see here. So for each point, you compute the k nearest neighbor. So here perhaps is the first, the second, or let's see, cannot write the second, the third. Okay, so you have the k nearest, for instance, here you have the k nearest neighbors, and you join with an edge each time you have a point and the nearest neighbor. And then the distance between 2 points in general is you compute the shortest path between the 2 points using the edges of this graph, and the length of each edge is the Euclidean distance. Okay, so perhaps the shortest path here is this one, and the shortest path, yeah, perhaps you use this one. Okay, so you compute all possible paths between the 2 points using edges of this graph. So this is a notion that is defined in general in different graphs. And for if k is too big, then you are going to have a graph that is too connected, so it will not reflect the original intrinsic distance. But in general, if k is well chosen, in the case when you don't have noise, this estimator of the geodesic distance is a good. It works well.
Thank you. Who else has questions? Rick.
Hi. I had a question about a slide that came a little later where you deformed that circular thing into a round circle.
Yes.
And I wondered, was that just, well, how was that done? Or what was that?
Yes, so I went very quickly there, but here, suppose that again, you have a formula to compute the distance between different points, and here you given 2 points, you compute all the path, and you raise to the power p each consecutive each segment. So you can compute using some little bit of graph of algorithm in graph theory, the best path between each 2 points and the length of each path. So you can compute the Fermat distance between points. The formula was before. Now, you have a matrix. So for each pair of points, so here you have x1 up to xn, x1 up to xn, and you have the distance between each pair of points, okay? Once you have a distance between points here, for instance, this point and these points will be not close under this definition of distance. Now, what you want to do is to project, so let's see in the next, yeah. You need to project, or say this is a function that sends each point in the original point cloud to a new point in this projection in such a way that the Euclidean distance between points in this projection will reflect the original Fermat distance, or the Fermat distance that you compute over the sample, okay? And of course, perhaps this cannot be done for each pair of points, so you are not reflecting this matrix, but there is an optimization process, and there is an algorithm called multidimensional scaling that is famous in graph theory and also in manifold learning. Multidimensional scaling, this is an algorithm that makes this procedure, this optimization, solve this optimization problem, try to find a projection of the original point cloud in such a way that this new matrix of distances between the points is reflected in this projection. So here I apply this algorithm.
Can you say anything more about the geometry behind that optimization idea?
Yeah, of course. The idea is that so let's go back. So what you have here is that each time, so this is an estimator, each time you have a long segment, this is going to, so for instance, if you use p equal to 2, this is going to be, it will have exponent 2. So each time you use a segment that has a long segment, the distance between the 2 points will be big, okay? So in this sense, if you let's go here, if you compute distance between these points, so between points here, this point and this point, since you're using a segment that will have exponent 2 or 2.5 or 3, then these 2 points here will be at this distance, for instance, okay? So in some sense, you are deforming this area that is empty in the middle, and you are obtaining this cycle, okay?
Okay, thank you.
Thank you for the question.
Okay, it's almost going to be time to start our next talk. So if anybody has any further questions, I'm sure Ximena would be happy to correspond in the chat or by email, or we can chat during one of the breaks. So let's all thank Ximena again, and we'll turn towards the next talk. Everybody has a 1-minute break.
Here, let's